Hi, my name is Ricardo, and I'm your host of Math Matters, and today I'm here to talk to you guys about encryption. So encryption overall is just protecting your information such that only you and maybe a trusted, person or party can view the protected information. And most importantly, it's protecting your information so that, a spy or someone who intercepts your protected information has no way of decoding it and no way of understanding it. So this relates to a lot of private information we have out there. Anything from money to personal information like your address, even your name, can be protected. Now, it can be protected both in the physical world and in the data realm, right? With, computers, on the internet especially, we have a lot of information that has to be protected, and we have to know how that data is secured. So, in the physical world, it's a lot simpler. I'm going to use the physical world as an example just to provide the shift over to how we use mathematics to protect the data we all hold most valuable. So in the physical world, we usually have something like a key to protect any kind of information. Usually when we're talking about information, something physical, it could be money. Money is a great example. I used a bank as an example. And with money, you want to keep that under, lock and key, for instance, or a combination. Now, for a lock and key example, the great thing about a bank and the money scenario is that for a bank to have one key, there only needs to be the transfer of a lock to every customer. So the key can be kept secret, and it never has to be exchanged. Therefore, there's no fear of it being lost or being intercepted. If you have to physically transport this key to a customer, physically transporting that is hard because you get hijacked and that key could get stolen. So you want to keep the key in the bank. You also have locks. So you could do two things. You could have locks in the bank, and people could go to the bank, put their money in, lock it, and then only the bank could open it, or the person under the bank supervision. Or send the person a lock, have them lock a package, such as a box, have them lock it, ship it back to the bank, and no one in the postal service can open the box, right? Because the bank ships a key, a lock with a specific, combination or a specific key that can only be used, which is at the bank, never shipped. The bank ships a lock to a customer. The customer can then lock a box and ship it back to the bank. So this can have, money, anything in it, and when it's locked, it can't be opened, on the postal route, and only until when it gets to the bank can it be opened. And when the lock is shipped there, no one can open the lock, not that it matters, because it's open, because there's nothing attached to it yet. So this transfer is really important because this way the key is localized and no one can really access it. So we transfer this over to the data realm, and every instance of data has some kind of mathematical operation that's used to protect it. So usually, and in the examples I'm going to be talking about, the encryption method in information and in the data we all use every day has to do with math, specifically modular arithmetic or clock arithmetic. It's called clock arithmetic often, and I'm going to explain what that is. Clock arithmetic is a way of, it's an understanding of math that is a little obscure as to what the actual number is, but it's basically the remainder theory. So pretty much, the reason it's called clock arithmetic. Clocks, there's 24 hours in a day, but they only have 12 hours on them. That's because if you think about military time, for instance, if it's 18 o'clock, we here in the US would know that's 6 p.m. Well, why is that? Because 18, when you divide it by 12, it has a remainder, REM remainder of 6. So that's the clock arithmetic. Basically, for any time greater than 12, it's also within 0 to 12, because when you divide it, it has a remainder less than 12. That is our time. We have our times range from 0 to 12 and 0 to 12, and we have two 12-hour period and 24-hour time. But let's say you could have more than that. and numbers never end, although we have 24 days, let's say you could have a 50-hour time. So let's say it was 50 hours. Well, what time would that be in our 12-hour system? Well, you divide it by 12, see how many times 12 fits in there. It fits 4 times, because 48 divided by 12 would be 4. And then there's a remainder of 2 hours. So the remainder would be 2. And that's really what modular arithmetic is, even though it's not taught very often. Knowing how clocks work, knowing how the remainder works, is a great way of teaching modular arithmetic. Okay? So basically, the mod is the remainder. So 50 over 12 equals 4 remainder 2. And this remainder 2 is what we're concerned with. Because mod is basically saying, what is the remainder after you divide by this number? So that's the number following the mod. So this says 50, another way of writing it is 50 mod 12, and this means modular 12. 50 mod 12 is, after you divide 50 by 12, what is the remainder? 50 mod 12 is equal to 4. 2. That's a very good thing to remember, actually. When you're talking about mod 12, it's not how many times it fits in, but rather it's the remainder after you fit it in as many times as you want. And we can see a really interesting scenario, because there are many things that can equal the same number when you take a mod, right? So, for instance, 26 mod 12 is 2. 14 mod 12 is 2, because it's 2 more than 12. Even 122, because 122 divided by 12 is 10. And there's still a remainder of 2. So 50 mod 2 and 122, mod 12, mod 12, both equal 2. And if I tell you the answer, and I tell you what the mod is, if I tell you these 2 key pieces of information, the mod and the answer, you have no idea about knowing what the actual number was. That's just like our physical example. If you have the lock, how you locked it, the mod, how you changed it somehow, and the actual object, the answer, there's no way of knowing what's inside because you can't unlock it. You can't know how many times the 12 fit in before you added the remainder of 2. Even though you have the mod, you have the 2, you don't know what the answer is, and that's clock arithmetic. Obviously, mods can be any number, they don't have to be 12. 12 is just commonly known because that's how clocks work. So let's show another example of the data realm. Here, with 2 people communicating through the internet, Alice and Bob. Now, Alice and Bob both have 2 different pieces of information. Alice has a message. Her message is 123. Bob has the mod. So he has the mod to which he's going to take it, and the number which he's going to divide it by and then get the remainder. So instead of it being out of 12, it's going to be out of 15. So he tells Alice the mod is 15. He has no idea what the message is. Okay? He tells Alice mod is 15. Then she takes this information, circled in blue, uses it to calculate her remainder. So she says, well, 123 is 123 mod 15 means 123 divided by 15, that's 8 with I'm going to circle the remainder in red, with a remainder of 3. So she has the remainder. Now, if she just told Bob the remainder, and he has the mod, he would not be able to tell the message, because the remainder means it's some multiple of 15 and then adding 3. But there are infinite multiples of 15. For instance, 15 times 8 is 120, add 3 is 123. So 123, her message, divided by 15, she found was 8, and the remainder 3. But unless she tells him how many times the number goes in, how many times the mod goes in, and the remainder, there's no way Bob can solve it. So she has the remainder from the mod, she has how many times it goes in. It's a simple division problem, essentially. Therefore, Bob, using his mod, knows 8 times 15 is 120, and 120 plus 3 is 123. He uses these two pieces of information to find her message. Now notice, in cyberspace, no one has said what the message is. No one had to say the message, and the message was never written across this cyberspace. However, as often is the case, people can hack into this information. So say somebody's able to hack into the information, they can see a whole lot of things. So, we have a spy up here. Spy in the sky, who is able to get into the cyberspace. And they can see the mod, the number, and the remainder. And with these three numbers, they can find the message themselves. And because the mod was given to Alice, they can, if they're constantly monitoring cyberspace, if they're constantly watching for these numbers, first the mod is given, they see that, they hold that number, which means nothing by itself, and then the number of times it fits in and the remainder is given, and they use these two numbers to find the remainder. Because both were given over the same method, they can calculate the message even though the message was never given. And that's kind of where it gets very difficult to give your data over the internet. Because if you have a password, if you have any personal information, how can you, the computer you're using even, communicate with the server of the company or the server that you're trying to connect to securely if anyone can essentially access this cyberspace, right? That is what encryption seeks to solve, and that's what specifically RSA encryption seeks to determine. So, in my next video, I'll be explaining what RSA encryption is, and more specifically, I'll show an example of RSA encryption and how that is much more successful of transferring a message than this is. Hi guys, thank you so much for watching my video. It really does mean a lot. And if you enjoyed this one, I encourage you to watch the next video in my series. And hey, if you're done with the series, there's always more mathematics to learn. Because remember, math matters.